For my first topic in my Module 3 Mastery assignment, I'm going to be talking about finding the sum of geometric and telescoping series. A telescoping series has terms that collapse or cancel each other out, while a geometric series has a pattern that is to multiply by a constant called the common ratio. This symbol, the green symbol, is called a sigma, and it's a way to express the series. It represents the summation. So when we had sequences, when you had the numbers, they were separated by commas, but now instead of commas we have the plus signs because you're adding all the terms together. This n equals 1 is our lower limit, and that means whatever n is equal to is the term we start with. And this upper limit is the ending term. And so right now it's infinity because the summation will never end. Our first example problem is going to be on geometric summation. The formula for a geometric series, is the beginning term a naught over 1 minus r, and r is our common ratio. If the absolute value of r is less than 1, then we know that the series converges. But if the absolute value of r is more than 1, we know that the series is divergent. This problem wants us to find the sum of the series from n equals 1 to infinity of 4 to the nth power over 5 to the nth plus 1 power. We know this is a geometric series because a constant is being multiplied by n. This constant is 4 over 5. The first step to this problem is to simplify. We can simplify this to give us a more clear version of the series to show us what the common ratio will be. So we have the 4 to the nth power over 5 to the nth plus 1 power. Now we can separate the bottom portion, the denominator, to be 5 to the nth power times 5 to the first power because it's equal. And when we simplify that farther, we get 1 over 5 times 4 over 5 to the nth power. So we know that r equals 4 over 5, but before we can find the answer, we also need the value of the first term. Now, because the first term is n equals 1, we will be plugging in 1 to find the first term. When we do plug in 1, we get 1/5 times 4/5 because 4/5 to the first power is just 4/5, and that gives us 4 over 25. When we plug this into the formula, we get 4 over 25 divided by 1 minus 4/5. We can say that this is the same as 4 over 25 times 5 over 1 because 1 minus 4/5 is 1/5, and when you divide two fractions, you take the first fraction and multiply it by the reciprocal of the second fraction. So when we do this, we get 20 over 25, or our summation 4 over 5. Now, we already have all the information we need to find convergence or divergence. We know that the absolute value of r is less than 1, so we already know that the series converges. The next problem I'm going to be talking about is based on a telescoping series. Remember, in a telescoping series, as terms are listed, they're canceling each other out, and the summation is whatever terms you're left with. So our example problem wants us to determine the sum of the series from n equals 1 to infinity of ln times 1 plus 1 over n. The first step of this problem is to simplify. We can simplify this to ln times n plus 1 over n, which just equals ln times n plus 1 minus ln times n. And because we have this minus right here, we can tell that it's a telescoping problem more easily now. Our second step is to start writing down the terms. Our first term, when we plug in 1, because that is the first term we're looking at right here, we get ln times 2 minus ln 1. We add this to our second term. When we plug in n equals 2, we get ln 3 minus ln 2. And then we add that to our third term. When we plug in n equals 3, we get ln 4 minus ln 3. And then for our fourth term, we get ln 5 minus ln 4. So we can already see that the terms are collapsing even without my marks through them. So now we need to list the summations, each term. So we have S1 is equal to ln 2 because negative ln 1 is just 0. So we are left with ln 2. And we have the second term is equal to ln 3 because when you have these two terms added together, we see that already we have ln 2 canceling out. So we're just left with this negative ln 1, which equals 0, plus ln 3. So we're left with ln 3. Our S of 3 is equal to ln 4 because when we get to the third term, we see that ln 3 has canceled out. And so now we're left with our 0 plus our ln 4, which gives us ln 4. Our S of 4, when we add all of these together, we see that ln 4 has now canceled out. And so now we're left with our equals 0 plus ln 5, which leaves us with ln 5. And we already know that ln 5 is going to cancel out because as soon as you get to your first term that has both of the terms inside of it canceled out, you know that every term after it is going to be canceled out eventually. So from this pattern, we can see that S of n is equal to ln times n plus 1. Because if we plug in for S of 1, we get ln 1 plus 1, which gives us ln 2. If we tried S of 2, we get ln 2 plus 1, which gives us ln 3. If we did S of 3, that would give us ln 3 plus 1, which equals ln 4. And if we did S of 4, that would give us ln 4 plus 1, which is ln 5. This formula will help us find convergence and divergence, but the sum, which is what we're mainly being asked to look for, is what is left over after everything has been canceled out. So the only thing we have left over is this negative ln 1 or just 0, like we have right here. Now, the convergence and divergence, in order to find this, you need to set up S of n as a limit. So we have the limit as n approaches infinity of ln times n plus 1. When you try to plug in infinity for n, you know that ln just keeps getting bigger and bigger and bigger and bigger and bigger and never reaches a value. So this will be divergent. The next topic I'm going to be covering in my mastery assignment is the ratio test and the root test. The ratio test and the root tests are ways to find whether a series converges or diverges. And the ratio test and the root test can both be used on any series. For the ratio test, if the limit of the absolute value of the ratio of the n plus 1 plus n term and the nth term equals L, the series converges absolutely if L is less than 1, diverges if L is greater than 1 or infinity, and is inconclusive if L equals 1. For the root test, if the limit of the absolute value of the nth root of the nth term equals L, the series converges absolutely if L is less than 1, diverges if L is greater than 1 or infinity, and is inconclusive if L equals 1. Our first example problem is on the root test. Our formula for the root test is to set up the series, but change the n's to n plus 1, substitute n plus 1 for the n's for the numerator of the limit, and for the denominator you keep the series the same, and you divide these two as the absolute value. And if L is less than 1, we know that the series will converge absolutely. If L is greater than 1, we know that the series diverges. And if L equals 1, there's no conclusion and we have to use a different test. Our example problem is asking if the series from n equals 1 to infinity of n squared over 3n factorial converges or diverges. Now our first step is to plug it into the formula and solve. There's really only one step. So when we plug it into the formula, we get the limit as n approaches infinity of the absolute value of n plus 1 squared over 3 times n plus 1 factorial. We plug the n plus 1 into the original n's in our original series, and we multiply that by 3n factorial over n squared, because this is the same as dividing it by the original series n squared over 3n factorial. We can simplify this to be n plus 1 squared times 3n factorial over 3 times n plus 1 factorial times n squared. You can simplify it more as n plus 1 squared times n factorial, because that's what 3n factorial will be, over 3n plus 1 times n factorial, because we had to pull this n factorial out in order to cancel it out in order to solve the limit, all multiplied on the bottom by n squared. So these two n factorials cancel out, and so we have the limit as n approaches infinity of the absolute value of n plus 1 squared over 3n cubed plus n squared. What we did to get the 3n cubed plus n squared is we distributed the 3 and then multiplied everything by this n squared. So when you do the calculus, you're left with 0, which is less than 1, so we know that this series will be convergent. The next problem we're going to be looking at deals with the root test. The root test is most useful when the nth term is being raised to the nth power. Our little formula for this is that for any series, you need to find the limit of nth square root of the absolute value of that series, and that will give you your L. If L is less than 1, the series converges. If L is greater than 1, the series diverges. And if L equals 1, the series is inconclusive, and you need to use a different test to find convergence or divergence. So our example is asking if the series from n equals 1 to infinity of n squared plus 1 over 2n squared plus 1 all to the nth power is divergent or convergent. All we have to do is plug it into the formula and solve. So when we take the nth square root of this series, we're left with n squared plus 1 over 2n squared plus 1. And we know that there is an imaginary 1 in front of this n squared. And so we have the limit as n approaches infinity of n squared plus 1 over 2n squared plus 1. And since our variables are raised to the same power, we can take the coefficients of that to give us our limit answer. This answer is less than 1, so we know that our series converges.